All right, thank you for coming to my talk. This is message handling with Boolean Algebra. The alternative title for this talk, much longer than could reasonably be submitted, The Unreasonable Effectiveness of Boolean Algebra in Software Design, showing the particular application of a message handling library, which we'll see, with a small excursion into the roots of programming. Some front matter. Please ask questions at any time. You're going to see actually a lot of code. Hopefully, it's actually, in the end, all pretty simple code. You're going to see most of the code that makes up this library. It's mostly East const. If you spot the West const, you can win a prize. The prize being the respect of your peers. Also, I gave a talk last year at this conference where people found the code hard to read. I don't want that to happen again. The irony here is that my wife is an accessibility expert. She's a web developer who's currently doing an accessibility audit. Accessibility matters, and it's for everyone, right? Not just for folks who have what we might think of as permanent limitations, but limitations are temporary, like I might sprain my wrist, or situational, like I might have to carry a baby or be in a loud room. And even if we are completely sound of limb, keen of eye, accessibility, we interact in a physical and digital environment every day with 1,000 things, 1,000 invisible design elements, which make our lives better because they were created with accessibility in mind. So accessibility really is for everyone. And I've started doing dark on light, as you can see, because that's optimized for you folks in the room, and the YouTube folks can just cope. All right, so this talk is about the design of a message handling library. I'm going to show the details of that. We're going to start off seeing the very declarative way this library works, specifying messages, fields. And then we're going to talk about how we recognize a message given data off the wire. We want to run a predicate on it to find out what kind of message it is. And then we'll see how to compose those kind of elements in the library and simplify those compositions so that at compile time, we get all that simplification, and at runtime, we do the minimum amount possible. And the application that I work in is the embedded space. So we are talking about very low level inside the CPU package. We're talking about messages which consist of bits, not even byte boundaries, but fields inside the bytes. And this is a really talk that builds up with simple ideas upon simple ideas, and by the end, we get to somewhere really quite nice. So yes, please ask questions at any time. This is my thanks slide to Augustus de Morgan and George Boole, two names you may know. How many people here learned Boolean algebra in formal education? Yeah, pretty much most of us. And I'm guessing the rest of us just learned it as we went along, picking it up on the job. It's something we use every day. We're dimly aware. It's underlying everything we do, but most of the time we don't give it a second thought. But how this started was my colleague Luke just put this one-liner issue on our repo and said, hey, I'd like to be able to factor these matter expressions into sum of products form, right? This led me down this rabbit hole. So yeah, I went down the rabbit hole. Luke puts this one-liner up. I go away for 3 weeks. I end up rewriting the library, coming back with something that does this and a whole lot more. This is kind of how my life goes. So let's start out with a quick introduction to the library. You're going to see some code. The first thing is a message field. I'm guessing many of you have code that might do things like this, message handling. So in this library, a field is a human-readable name, right? A type that is going to use to interact. That type is not the layout, but it is the type that gets passed around to functions and whatever. And then the layout of the field is defined by one or more locators. And conventionally, we specify this with a word index, a most significant bit, and a least significant bit. Remember, these are bits. And that's inclusive. That's conventional in the embedded space, at least in the space I work in. So here's perhaps an example which some people might be somewhat familiar with. This is the IPv4 header. And this is straight from Wikipedia. And we can see it has some fields in it, which are sub-bytes, right? Version fields 4 bits, internet header length 4 bits, et cetera, et cetera. Those 4 fields in this library look like this. These are type declarations. You can see that the first parameter is the name. Then we have the type. And then we say where it's located, right? So this library has a very kind of declarative style. These are just defining types. So that's fair. OK, we've got some fields. Fields have 2 methods, right? They have extract, which you give it a range, the data, an array of bytes, an array of uint32s, whatever. And you get back the type of the field, the value. And insert works the other way, as you might expect. You give it the range, and you give it a value to write into that range, and then the field can insert its value. Of course, notice that a field is an empty type. It's the layout, right? It's a definition. It's not data. The data is in the array, and we use the fields to read and write it. So a field separates the spec, which is the name of the type, and the locator, because potentially different fields with the same name could be located differently in different messages, right? So we're separating that. The range is random access, yes. Yes? I have an extra, oh, yeah, you're right, I do. That should say static auto insert trailing type void. Thank you. Hopefully that's the one mistake in the slides. We will see. So one convention is to locate fields by dword, most significant bit, least significant bit. But another convention that's common in the embedded space is just to use the raw bit offset. These both amount to the same thing. The library supports both. You can see that flags in this case is at offset 48, right? Or alternatively, it's in the dword index 1, offset 16. Right? These say the same thing. There is one more use case we have, which is that a field might actually be split across multiple locations. So in this case, the 2 nibbles of the field are in disjoint locations, but it's still a uint8t when you read and write it, right? So that's another use case. We just put multiple locations in there, still nice and declarative, right? Everyone happy with fields? OK, so given some fields, it's fairly easy to say what a message is. A message is a named collection of fields. And we can say, like, the IPv4 header is a message called IPv4 with a bunch of fields. Now, that's still just an empty type. That's defining the layout. When we put that together with storage, with a random access range, we get a message instance. And the fields have those extract and insert methods. The message has get and set methods, which delegate to those extract and insert methods. And so this is what it looks like. And as you might expect, the underlying data can either be owned by us. If we're typically sending a message, we're making a message, we own it, we send it out. Or if we're receiving it off the wire, we just want to overlay that layout on some data that came off the wire, and we got a view of it. So either way works. All right, all good. Yes?
Start lifetime and all this stuff.
Yeah, well, yeah, if you're right, if we just had a struct and cast it, then we'd have to do the start lifetime. But the extract and insert methods, or the extract method in this case, it deals under the hood with things like, I can't remember exactly, but effectively a memcopy, a bitcast, something like that. So yeah, those things aren't alive in the message, but they come out safely when we read them out. So this is a nice interface, right, to start with. We can ask compile time questions. Like you saw a couple of slides back, when we say we want an owning message with this layout, like the machinery knows how to, what size that should be, because it can just look at the fields and all their sizes, and it can figure that out, right? And we can ask all these compile time questions. Okay, that was just really all you need to know about fields to go forward and messages. Now we're going to turn our attention to how do we actually match these things at compile time? How do we run predicates, right? So a matcher, what I call a matcher, is a predicate on the, that takes a message and returns true or false. And this is a sort of prototypical concept for it. So we call, a matcher in particular is a function object, right? So we call it with a message, and it tells us whether or not that message matches whatever we want to match, right? Here's an example of a matcher. We're saying, you know, does a particular field have a particular value, right? So we just get that field out of the message, compare it with the value. That's an empty function object. That's a matcher, okay? Yeah, it's empty. In fact, we can take that equality matcher and we can genericize it a bit by passing in a relational operator, right? So a relational matcher in general is parameterized over an operator. The operator you just saw was stood equal to, right? But we can also put in stood less, stood greater, you know, all those relational operators, those function objects from the standard, they work the same way. We just run them like that. Everyone happy? All right. Well, matchers are functions that return Boolean values. They are isomorphic to Boolean values themselves, right? The value x is isomorphic to a function taking nothing and returning x. And so we normally compose Boolean values by using and or not, right? What we need to do here is just provide class templates that wrap the matchers, implement that function call operator in terms of the underlying matchers, and we'll build up. This is kind of like, you know, baby's first expression template sort of stuff. This is, you know, very small universe, Boolean algebra. Here is what that looks like for the and matcher, right? We're going to take in two matchers, L and R, left and right-hand side. Our function call operator is going to call those matchers, and guess what? And together results, right? So I bet you can guess what OR looks like. It's exactly the same, right? Except for, obviously, we're ORing together results. And not even simpler. One matcher, and we just return not result. These are, I hope this is like easy to follow. Seems pretty obvious so far. Okay. Given those class templates, we can overload operators. In my code, I tend to use the alternative tokens, which is why this doesn't say double ampersand, double bar, and operator bang. But they're just the same. So we're going to do the obvious thing. When we use the and operator, we're going to return an and class template. Or is or, not is not. Okay, all right. That's the setup, okay? So we have ways to define fields and messages. We have ways to match on those messages. We have some ways to combine matches. So let's take a look at how the library is actually used in context. Wall of code, but let's just go through it. We're defining a type. Right? We're defining a field. The field is the type of the message, right, in this case. And then we're defining a message layout. It has that field and probably some more fields I didn't put on the slide, right? Then we're defining a callback. A callback links together a message layout with a matcher. And line 8 here, that's a DSL. That's a little DSL that's making a matcher. So line 8 is a matcher value. What kind of matcher is it? It's the matcher you saw. It's the equality matcher comparing the type field to 42. And it's a callback, so of course we have a callback function on line 9, and that's going to take a view of the message. And then line 12, we have a handler that encapsulates actually multiple callbacks. There's only one on this slide. And when we tell the handler to handle data, line 17, it's going to go through all of the callbacks. It's going to run their matches. If their matches return true, it's going to call the callback associated with that matcher, the callback function. Clear? Yes? So at this point, I'd like to ask, like how many people have done something like this in their code? This is, I think, a fairly common use case, right? We got a few people, yeah. No, Roy was just putting his hand up to, that wasn't a question, that was a show of hands. That's all right. Okay, yeah, and here is the matcher DSL. I mean, we've got overloaded operators, we've got integral constants effectively with _c, and those ands and ors in there are the overloaded operators that are returning the and matcher, the or matcher, etc. So this is what it looks like to use. Okay, now, everyone in here knows Boolean algebra. I just wanted to make clear the notation I'll be using, because there are different notations, So I'm going to be using wedge for and, v for or, and not sign for not, just like this. Everyone good? Yes? Okay. Well now, okay, so we've made this system, and we've got an expression template, right? And our expression template might look like, it's a tree, basically. It's a Boolean expression, which we can look at as a tree. And all those matches are sort of compile time values. The information's in there at compile time. We want to make sure that evaluating this at runtime is as simple as possible. And I should point out at this point that this library, this matcher library that we're building, interfaces with a couple of other libraries. So in particular, when Luke put that issue in the repo, he was thinking about the matcher library being downstream from another library which kind of does indexing on the fields, right? So there might be an upstream thing which indexes some fields so that by the time we get to actually calling one of our matches, we might know that one of the fields is already 42, right? Because we've indexed on it. But we might have some extra matches to run, right? So there are multiple things going on here, and this is designed to kind of fit in with other libraries. So here are some example type problems. At this point, I sort of took a step back. I have this, nice looking library. It's nice and declarative. But now I start to think about, well, I know things as a human. How can I tell this to the compiler? If I see someone who's written less than 5 or greater equal 5, I know that's always going to be true, right? We know that as humans. If I see less than 5 and less than 7, I know that I don't need to evaluate less than 7, because if you're less than 5, you are necessarily less than 7. And if I see not less than 5 and greater or equal 5, I know they're saying the same thing, right? So I use the Feynman problem-solving algorithm. Who's familiar with that? So the Feynman problem-solving algorithm, step 1, write down the problem. Step 2, think very hard. Step 3, write down the solution. It sounds funny, but you'd be surprised how much step 1 is important. Write down the problem. And so this is the problem, right? So then I went away and I thought very hard for a few days. So the problem is, again, back to that tree diagram, how to simplify that at compile time in a generic way. Okay. Now, of course, like you all, I know the normal rules of simplifying Boolean algebra, You can go to Wikipedia and you can find them all, just to make sure you haven't missed any. But we know them just because the last slide showed us humans, we know how to simplify that stuff. But how can we tell the library in a generic way about that stuff? Well, I took a step back and I started out simple. I thought, well, we're using Boolean algebra, so let's start with the basics. Let's define true and false. And these are functions, so I called them always and never. And as you can see, they are trivial. Always, you give it a message, and it always returns true. and never always returns false. So these are the atoms of Boolean algebra, right, in our world. Start with the basics. Okay. Well, now, if I can tell the compiler that I know that C is always going to evaluate to true, I can replace that with an always T. And if that's the case, I know it's part of an OR expression. If you put true in an OR expression, you're always going to be true. And if that's the case, I know that that true's in an AND expression. I just need to evaluate the other leg of the AND. The whole tree would collapse if only I could generically tell the compiler what I want to tell it. Okay, well, here's an obvious step. Let's try and write a simplify function. So we'll want to simplify this tree. So let's start. So the default simplification is nothing, right? This is the fallback. And it's just returning the matcher because I couldn't simplify it, right? So, well, okay. So now I can think about how do I simplify an AND? And I can write this. This is sort of the regular Boolean algebra rules, right? First of all, I simplify left-hand side and right-hand side. Then I can write this multi-arm if const expr. If either of them are never, well, I'm in an AND, so I have to, that evaluates the false, right? Otherwise, if either of them is true or always, I'm going to return the other side. Otherwise, I can't simplify any further. I just return an AND with the branches simplified. Okay? Yeah, Roy.
The compiler knows that this overload is more special or more specific than the previous one, so there's no collision.
That's right, yeah. Because the compiler knows that, so this catch-all is less constrained than this function, this overload function for AND T, because I've got the AND T in there. Okay. And similarly for OR T, I didn't show an OR T, but you can write one for OR T, et cetera, et cetera. Well, okay, you know, this is like, I started down this route, and then I'm like, well, there's a lot of stuff to cover, right? And not only is there a lot of stuff to cover, we have to write every function to deal with commutativity because left-hand side and right-hand side could be swapped. It's a lot to do. And I went down this route, and I'm like, this can't be the best way. Okay, yeah. And this doesn't even solve one of my problems, which is how do I deal with less than 5 or greater or equal 5? These are two different types, right? How do I know that this simplifies to always? Okay. Well, I said, first of all, let me customize not, right, for these. So I don't always want to return the not node. I might know in this case that these two things are complements of each other. And if I could let the compiler know these two things are complements, then it could use the normal rules of Boolean algebra. So instead of always returning a not t, I write myself a not function. And again, the default thing to do is just call the negate overload. And the negate overload does the obvious thing, wraps a not t around whatever I give it. Yes? Of course, now there's an obvious extra overload we can give, which is if you're knotting something that's already a not, you don't need to wrap it twice. You just unwrap it, right? That's kind of obvious. Suggests itself immediately. Okay. We can negate or complement the relational operators by effectively complementing their operators, right? The inverse of less than is greater than or equal, and vice versa, et cetera, et cetera. So we can write negate for a relational matcher, and all we need to do is write this inverse opt, which is effectively like a half a dozen if const exprs, right? It's a very simple function. You can imagine how that goes. Great. Now we've genericized the idea of complement. So our library actually understands things besides just what we defined as a not t. And so when we give it this expression, it now knows that these things are complements of each other and can use normal Boolean simplification that we saw before because it knows that A or not A is always, right? Okay, any questions at this point? We're beginning to build up. It's all, I hope, baby steps at the moment. We're beginning to build it up. This next problem is I found a bit trickier. Less than 5 and less than 7. Again, don't need to evaluate both sides because I just need to evaluate less than 5 because that entails being less than 7. All right. I like to put quizzes in my presentations. Here's a quiz for you. The answers should be very easy. Shout them out. There's no tricks. If I have a thing of type A, and I have a function from A's to B's, can I get a B? Yeah. Yes, absolutely. There's no tricks. You all know the answer, hopefully. You just call the function, right? Okay, slightly different. If I have an A, and now I have a function from A's to B's, can I get a pair of A and B? Absolutely. You've got the A and you make the B using f of A, right? Now you have a pair of A and B. If I have a variant of A or B and the same function, now can I get a B? Yes. Absolutely again, yes. There might already be a B there in the variant, in which case I'm done. Or if there's an A, I'll call the function again. Right. These are all trivial questions, right? Yes. What am I talking about? You just did Boolean algebra. You thought I was asking about functions, but you actually did Boolean algebra. Let me reinterpret these questions for you. What does that function arrow mean? When you have a function, what does that arrow mean? It means implies. It is a Boolean operation. It is implication. It is the same thing. Let me reinterpret those questions. When we say in C++, I have an A, what we're saying is A is true as a proposition. When we say I have a function from A's to B's, we're saying A implies B is a true proposition, right? I want to be careful here. I could just say A implies B, but I'm deliberately saying A implies B is a true proposition because the implication operator is just like the and or the or operator, and it gives us a new expression which is itself, has a truth value, right? And so we ask, is B true? That's saying, can I obtain a B, right? When I say, can I obtain a pair of A and B, I'm asking the question, is A and B a true proposition with the same precedence, right? The same precedence. And when I say I have a variant of A or B, I am saying A or B is a true proposition. And again, A implies B is a true proposition. And now I'm asking again, is B true? There is a direct correlation between types in C++ and a Boolean algebra interpretation. So, maybe some of you knew that, but maybe some of you were just working off your regular knowledge of C++, right? You knew these answers. Maybe you didn't realize that you were doing Boolean algebra, but you knew how functions worked, right? So that's what functions mean. That is the Curry-Howard isomorphism, right? You've heard of product types and subtypes. Function arrow is implication. And yes, you know how this works. The questions were trivial because you know how functions work. So all we need to do is sort of unpack that implicit understanding and map it to actual Boolean algebra. Okay, well, what is implication? Here is the truth table for implication, right? Here's a truth table for and, which I'm assuming everyone's familiar with, for or, and on the far side for implies. So it is a operator, it is a proposition, just like and or. You'll notice, if you sort of think for a sec, it's equivalent in value to the proposition not A or B. Okay? Yeah, and it's sort of natural, and Roy, I think, just mentioned this. It's natural to think of implication of if A is true, then B is true. And that's okay, you know, but it's sort of, implication is a proposition, and it can be easier to think of it that way. But it's a proposition just like and or are composing things. It's an operator. Now, there are a couple of things I want to point out that are axiomatic, if you like, or just fall out of the truth table, and the fact that these are always true. So anything implies true is always a true proposition. And false implies anything, likewise, is a true proposition. And we can see this by looking at the truth table for implication. I've grayed out the lines that don't matter. Anything implies true. The truth table tells us this. False implies true is true. True implies true is also true. And the second fact, false implies anything. Again, we can see from looking at the appropriate lines of the truth table. False implies false is a true proposition. False implies true is also a true proposition. This is very difficult to intuit as a human. False implies anything. I, as a human, and perhaps some of you as humans, find this a bit tricky to intuit, right? So there are a few ways I can try to explain this. All unicorns have pink polka dots. That is a true proposition. That is one way to explain it. This emoji is wrong. Sorry. The people who made the emoji don't know this fact. But then all unicorns are sort of bluish gray is also a true proposition. So maybe they're not so out of touch. Yeah, unicorns don't exist. So anything we say about them is true. Okay, that's one way to put it. Let me try another way. If it's raining, the ground is wet. That is an implication statement that has a truth proposition. This is another way of explaining implication. The question to ask yourself is, what would make that a false statement, right? It would only be false if it's raining and somehow the ground isn't wet. The ground might be wet and it's not raining. The ground's wet for some other reason. It doesn't change the truth of this proposition, okay? Because the ground, might have sprinklers on. It might have just been raining and now stopped. Ground's still wet. Proposition's still true. So in other words, it's not raining. False on the right-hand side. Oh, sorry, left-hand side of the proposition. The ground might still be wet. Yet another way to look at this is in terms of sets. So the set of times when it's raining is a subset of the set of times when the ground is wet. Okay? These are sort of three ways to explain the same fact, the same mechanism of implication. Does anyone have any questions at this point? I see no hands. Okay. So, like I say, I went away, I thought for a few days, and I sort of had an inkling that implication was what I wanted. And I looked again at the truth table for implication, and I noticed that if I can strike out the line where the implies proposition is false, in other words, if I can warrant that a certain implication is true, I can take out the third line of this truth table. And then what happens? We can see that A and B is identical to A, and A or B is identical to B. That seems useful. That's a simplification I can use. All right, so let's look at some code that uses that. This is what we were really intuiting when we said we have less than 5 and less than 7. We don't need to evaluate less than 7 because we know that less than 5 implies less than 7 is a true proposition. So let's code that up. Let's make an implies function. What's the default going to be? It's going to be x implies y if x is the same as y, right? In general, two unrelated types, one doesn't imply the other, but if they're the same, that implication is true. That's easy enough to code up. It's a one-liner. Let's make some more fundamentals. We saw them on the previous slides. We saw them in Boolean Algebra. Here they are in C++. This is anything implies true is a true proposition. And this is false implies anything is also a true proposition. And the third one here is just an ambiguity breaker between the first two. So we have to say to C++, well, you can't choose between those two if I tell you to evaluate false implies true, so here's the overload for that case, right? Just an ambiguity breaker. So far, pretty much everything is 1 line, 2 lines, very simple functions. This is how I like my libraries to go. Okay, how do we do and or? So if we have the proposition x and y implies a, well, we can do some Boolean algebra manipulations. Here we're using the fact that implication is the same as, x implies y is the same proposition as not x or y, right? So that's the first transformation. That's lines 1 to 2, just using the truth table. On line 3, we can simplify, we can push the not in using De Morgan's laws. Everyone familiar with De Morgan's laws? Who's done Boolean algebra? I'm seeing some nods. If not, you can find them on Wikipedia, of course. Then we can kind of duplicate that A because we're using the idempotency of or you might think of it as sort of distributing, maybe. But lines 3 and 4 are saying the same thing, right? We're just doing simple transformations. And finally, line 5, we can use the truth table implication again to go back from not x or a is the same as x implies a, and not y or a is the same as y implies a. So this is telling us the Boolean algebra, and in C++, that looks like this. When we're simplifying when we're writing the applies function for an and, L and R implies M if L implies M or R implies M, right? That's what we just wrote here. Line 1 is true if line 5 is true. And that's a very simple translation to C++. And the same, in fact, an even simpler few lines of Boolean algebra gets you to the implies proposition for or. Again, one-liner functions. I love one-line functions. These are great. Now we can write an implication we can warrant the truth of an implication for 2 relational matches if the operation is the same, right? So this is saying less than 5 implies less than 7, for instance, right? Well, that's true if and only if 5 is less than 7 or 5 is equal to 7, right? So we can say it's true if they're equal or we run the operator. And the equality is just covering the case when x implies x. We can go a little bit further because now we can write implication between different relational operators where that makes sense. Less than or equal x implies less than y if x is less than y, right? That's one example. And there are a few others, like you can intuit that you can write the same thing for greater than equal, stuff like that. So this is what, remember maybe 20 minutes ago I was talking about we can write the simplification for and. This is what it looked like on the previous slide using regular Boolean algebra, right? We sort of hard-coded the idea that we have to look for nevers and always on the right-hand side or left-hand side of the and or the or. But now that we have implies, we can use, striking out that line in the truth table, we can ask, well, if the left-hand side implies the right-hand side is true, then I can just return the left-hand side, right? If the reverse is true, right-hand side implies left-hand side. The and collapses to just the right-hand side now. And if either side implies the negation of the other, I know that the and must be false. Otherwise, I can't simplify. So I'll just return the and as before with the simplified left and right-hand sides. Again, okay, more than a one-liner, but each case is a one-liner. And or looks just the same. Oh, I have another error on the slide that should take an or on line 2. I missed that one. Very, very similar, but it's kind of dual, right? So again, if either side implies the other, we return the other. If either side implies the negation this time, well, A or not A is always true. So instead of returning false, we return true in the or case. Otherwise, no simplification. Now we're getting somewhere. Now we're actually, this is going great. We've just written a few functions, and it turns out this is all we need. We've customized negate. We've customized implies in order to warrant the truth of it. We've got a few basic negation rules. We wrote x implies true and false implies x. We wrote that negation for not x is just x. And we've got these few short simplification functions now for and, or, and not. And all of the things of Boolean algebra, all these simplifications just fall out of this, right? The identities of true and false for and or, annihilators, idempotents, absorptions, all the rules you find in Wikipedia, they fall out. There are a couple of things that don't. Okay, so I should say De Morgan's laws aren't part of what we did yet. And distributive law is not used in the simplification because we didn't need those, right? But as far as simplification goes, we're done. We're done with just 2 customization points, like half a dozen functions that are very trivial. We now have the matched DSL. We have all the compile time simplification of those expressions that can be done, resulting in minimal work to do at runtime. And this composes with other libraries because actually the message library that I introduced at the start is an entirely separate library from the matching part, right? The relational operators, they're in the message library, right? Relational operators aren't really part of the Boolean algebra library. So you've actually seen 2 different libraries here that mesh together really well. The matches and the Boolean algebra, that's where we have complement and or not, negation and simplification and implies, right? And the message library is concerned with equality of fields, less than on fields, et cetera, right? And in turn, Luke's indexing library is concerned with something else, indexing on a particular field, and then coming down the pipeline to test matches or whatever. And these libraries fit together great. Luke has a talk about the indexing library. I didn't have time to cover it in this talk. Okay, so at this point, you have seen pretty much all of the code. That's the talk. I mean, I love it when this kind of thing happens. It's like an application of Boolean algebra or something very simple that we use every day, but we don't give it a second thought. But when we actually think about it and how to apply it, and just have a few insights, we build up in baby steps, and now we have a really powerful system that's incredibly composable. So a few important points I want to make. So A implies B has the same truth table as not A or B. But I don't think I could have done this in terms of not A or B. For the same reason that, we don't just have a NAND operator in the library. Even though the hardware only does nands under the hood, right? We actually find it useful to have and, or, and not. And it is useful to have implication for the same reason. We were using implication to warrant propositions as true to allow simplification. And not A or B is not in a good form for us to do that. There is a paper, Implication for C++, written by Dr. Walter Brown. He and I have corresponded. I've given him feedback. I think that would be a good thing for C++. And to the folks who think, well, it's just equivalent to not A or B, here is a use case where not A or B formulation would not have given the same outcome.
Why not?
OK, it is the same truth value. But you go away and write a library that somehow evaluates not A or B the way I've used implication, or allows a programmer to warrant its truth. It's much harder, I think. I'm not saying it's not possible. This is C++. But I think it's significantly harder, right? I've shown you a half a dozen one-line functions that give me this. Another thing I noticed about this a little later on is, did you notice that A implies B is a sort of true higher order function, right? Because we put things in the types, we're never actually evaluating the matches. We're just able to use them to simplify. Most higher order functions compose their functions, but they end up evaluating them, right? In this case, we're never evaluating them. We've actually composed the functions directly, which I thought was an interesting thought. You know, it's because we've done things in types, maybe. But this struck me as an interesting thought. OK, so I have a little epilogue here. We're getting close to time. We're gonna be good. It struck me after having done this a little while later that this implied an ordering between matches and maybe a new intuition for implication. So, you know, what does it mean for matches to be ordered? What does it mean for Boolean values to be ordered? Well, if they're just Boolean values, oftentimes we just think, well, false is less than true because false is 0 and true is non-zero or 1, right? And that's just a fact that we grow up with learning C, and we go on a merry way, and we never think twice about it. But when we sort of extend the notion of Booleans to functions, predicates, we can think of predicates as being on a continuum, right? Always is at one end, and never is at the other end. And in between are predicates that match sometimes and match don't. So what does it mean for ordering? Well, one sort of intuitive thing it might mean is that a predicate is larger than another predicate if it matches more things. Or it's smaller than another predicate if it's more constrained, so it matches fewer things. In an Euler diagram of sets, it looks something like this, right? So A is greater than B. A matches more things than B, which means that B implies A, right? Because everything that B matches is also matched by A. Now, this diagram might be that they coincide, right? That would also be B implies A, but it makes for a worse diagram. This is a clearer diagram. And now we can see why false implies X, because false is the matcher that matches nothing, right? It's the empty set. And that is a subset of any set, right? So false implies anything in this intuition because of this picture, right? Slightly different intuition to have for implication. Sorry? Yes, so we can define a partial ordering of matches, right? And this is what the code looks like. We simplify the matches, fine. Then we ask, does either one imply the other? If neither one implies the other, then there is no ordering between them. So we have to return unordered. But if one implies the other, then it's going to be less than or equal to the other. So we can use the spaceship operator on the implication propositions both ways around and that defines a partial order of the matches. OK, what else? Well, like I said, you have seen almost all the code actually in the match library. It really is that simple and that powerful. There are some things which are in there which deal with other use cases. Luke's original use case, if converting to sum of products form or disjunctive normal form, what that means is an oring together of and terms, right? Or possibly not terms. But at the top level, you have A or B or C or D, and where A and B and C and D could be themselves and propositions or further propositions, but propositions that don't involve or. In other words, we've bubbled all the ors to the top. When we have something in this form, we can treat it as a disjunction. So like you can say, I want my callback to occur if A or B or C or D. That's the same as saying, evaluate, separate out A, B, C, D, put them in a table with the callback, and evaluate them separately. That's why Luke had that use case. And this library does that using De Morgan's laws and the distributive law. So that's those other transformations. Luke has a talk from C++ Now this year. That is the talk. So, the takeaway for me here is that, first of all, in the design of a field and message library, it really helps to separate layout from storage and have owning and have views, and that's really powerful. The correspondence of Boolean algebra and type algebra is absolutely fundamental to programming. And I hope I've shown that just a little kind of insight into that enables fairly amazing compositional code. I'm really happy with this. And lastly, implication is a valid operation with surprising applications, right? Like probably most of you, I do not use implication in my day-to-day. I have a hard time intuiting implication compared to and, or, not, which are bread and butter, right? But when I sat down and thought about it, I realized implication was the key to this library. All of the code you've seen on the slides is available. This is an open source library. It's sort of a sub-library of Intel's compile time initialization and build library. And you can find it at this link. Thank you very much. Yes, question.
Yeah, thanks. Amazing talk. And you said that you like one-liners, right?
Yes.
Well, you actually have one-liners embedded throughout your presentation.
Mm-hmm.
It's not in C++. It's the math. The math is the one-liner.
Sure.
And
absolutely.
And I see it's your intention just translating the math in Boolean algebra to C++.
Mm-hmm.
And I think you can, with a few tweaks to like how the implies function works, you can get pretty close to how you would write math. Of course, you can replace the English with the Unicode. That's something you can do.
Sure.
And the implies function can also be infixed. And that way, it would read more natural to how the math formulation is. And what do you think?
Yeah, you mean like A dot implies B when you say it can be infixed. Yes. Yeah, we could make the C++ look more like math. It may surprise some of you to know that my formal math education ends with high school. I did not study math at university beyond what's in a regular computer science course of discrete math and stuff. So I use math, but I don't generally, like I'm not a category theorist or anything like that. But yes, thanks.
Yeah, thanks.
Bryce, I think your hand up was next.
So what can you do with the partial ordering of matchers? Can you do some, like if you've got a handler that takes multiple matchers, can you use it to do some sort of interesting reordering that gives you a performance benefit? Or
So I don't really know the answer yet. Like I said, this was an epilogue. I just noticed, like a couple of weeks after I'd done the library, I had this realization that actually this defines a partial order, and I thought it was a useful intuition. I don't really know all the use cases of it yet.
Yeah,
So-
it seems like in the case where you've got like a set of like multiple matchers, like you can potentially use it to do some sort of interesting transformation.
Could be. Could well be. Yeah. Thanks. Yes, David.
Hello. Is there an optimal normalization of your expressions such that the simplification is like better? Is there a...
Yes. So I think you're asking, your question is sort of pointing toward the realm of satisfiability, right? Which is, as far as I'm aware, NP complete. This doesn't do that. But for the use cases of this library, this is great. I haven't really thought too hard. Most truly gnarly expressions we would catch in code review, I think. They don't get that gnarly, but they do. It is important to eliminate some subtrees, which is what we do. General satisfiability is, I think, a much harder problem, and this library does not directly address that. Roy.
Hey, great talk. So first of all, with the upcoming reflection proposal and potentially the abilities to do like token generation or code generation, how will this look like?
I don't know, but I'm open to ideas.
Okay, so my basic thought was that these types of transformations of like expression trees is something that compilers do all the time.
Yes.
On a-
Yeah. In particular, concept subsumption is an example where compilers manipulate Boolean algebra, yes. I don't know how the major compilers do that. I don't know if they take a similar approach to that of mine, but possibly. There is one more question perhaps I can answer, which isn't asked by the audience, but I have been asked by folks, which is they see this library and they say, oh, can I use that for my financial application? I do a lot of that kind of thing with the fixed protocol or whatever. And there are two differences here. One, so you may be able to. I don't have that use case. Possibly you might. But two important differences I would note. One, we're dealing with things beneath bytes at the bit level. Generally, all application level protocols deal with bytes, right? So there could be a performance difference there. It could be faster to deal with bytes than to deal with bits like we have to. Secondly, there's, I think, an important use case for protocols in general at the application level, which we don't need, which is variable length arrays and corresponding fields which dictate their length, right? Those two things are differences between the use case for this library that I haven't embedded and the typical use cases in financial or application level stuff. So, you know, it's unlikely we would want to extend the library to support those use cases and incur that maintenance, given that we don't have those use cases. But they might work. So that's just to answer a question that I've been asked in the past. Yeah, okay, one more question, because we're at time. Go ahead, Roy.
So my intuition regarding the greater than 5 and greater than 7 was more around the set union and set intersection, the type of things.
Yeah.
Like allowable ranges and stuff. And I think Luke Valenti did like similar stuff on his safe integers library. So can you comment on that? Or
Yes, there is indeed another, I think, isomorphism between that kind of set interpretation and Boolean algebra and type theory. They in a sense, all speak different dialects of the same language, yeah. All right, thank you all very much.